Hello, everybody.
How's it going, Professor?
Doing well. How are you?
Doing well as well.
Okay, good. So you guys can hear me. You can see the screen.
Yes.
Awesome. All right. Well, start with the bad news. The bad news is for everybody. I graded all the midterms on Friday, and I don't even know how long I took. I think it was over 6 hours I spent grading those midterms. And what I did was every single point that I took away a point for each problem, I put a little comment sticky, just like I do on your homeworks, to explain why it is that I took away a point. And took a long time to go through and annotate everybody's test so that everybody would know exactly what happened. And apparently, nobody can get to those comments, which is immensely frustrating. And I asked IT to find out what happened to the comments. And the bad news is they just got back to me and said, we don't see any comments either. So I don't know what's going on with those comments. I did it exactly the same way I did it with everybody's homework. And they should be there, but they are not there. So until we can re-find the missing comments, yeah, this is very confusing because some people say they did see them on the homeworks 1, 2, 3, and 4, and I have some saying that they can't see them on homework 3 or 4. Next time I set up an assignment, there's a good idea. Try a different browser. I don't know if that makes any difference. I will go through when I set up the next homework assignment and see if there's any buttons or radio checkpoints or something that would prevent you guys from seeing the comments. But that being what it is, I apologize. The whole point of going through that was for a learning experience. But I'm not sure if we're going to be able to get those back or not. So in lieu of that, I thought the next best thing we can do is to, if everybody has their hard copy of what they turned in for their midterm, and we can walk through the test, and I will walk through how to solve each part of it. And then you can see what I did that may be different than what you did. And hopefully that will make this midterm a learning experience, which is really kind of the overall point. So that's what I'm going to do. I solved it I originally solved it on just scratch paper, but I transferred all that to the test so you can see what I'm talking about as I'm talking about it. And if anybody has any questions like, why did you do that? Or I did this, and is that okay? Or is that not okay? Please just pipe in and we will go over the test. So
I just have a very quick question. So like on the grading part for the assignment, like for the assignment and the assignment submission for the test, it says 0.
Yes.
While like for the okay, so that doesn't affect the grading.
Not at all. Not at all. What I tried to do was the test is the test. So the test was out of 50 points, and you all can see what you got out of 50 points. But as I explained before, if I just graded off of that test, then that would just be absolutely horrible, because it's very, very easy to miss just one number, and then the whole problem is wrong. So that's not fair to anybody to just grade off of the test. So that's why I had everybody upload their work to an assignment, and then I could use the assignment to give partial credit. But the assignment was always 0 out of 0.
Okay.
That makes sense?
Yeah, thank you.
And then the whole other point was so that I could write comments on it and tell you where you missed some points.
Right.
Okay. Oh, Shayna had a very good question. I'll pull that up for you. That's an excellent question. Class roster. The average for this midterm was 36.5, 36.5. That was the average score. And the standard deviation on that was 11.6. So I'll talk a little bit more about that after. Ashley, there ain't no way I'm doing more than one class in a semester. So the answer would be one. I have one section that I teach. Remember, this is my fun hobby. If I try to do more than that, I would kill myself.
Professor, did anyone get a
yes?
50?
Did anyone get a 50? No.
What was the highest score?
I am looking. There was 149 and there were a couple of 40, like 348s.
Okay, got it. Thank you.
Okay. All right. So let's go through this because I actually do have a lecture too, all ready to go and excited about. But I want to talk about this first because I want to, I mean, really the whole learning experience is to see where you went wrong or misconceptions now before we carry those over into the next half of this semester. Okay, so without any further ado, here was the problem. We had a beam that is 30 inches deep, 18 inches wide. The steel was given to you, 8 number 9s, and D wasn't exactly given to you, but the dimensions to the steel were. And so what I asked for was the nominal capacity, check the minimum steel and minimum beam width, and find the allowable moment capacity. So this is 100% an analysis problem. Everything is given to you. So we start by finding nominal capacity. What is the capacity of the steel in tension? So the area of a number 9 is 1 square inch. I have 8 of those times 60 KSI, 480 kips. And then I solve for okay. I have a private question, I'm sorry, but I'll get to that. I'll get to your question. Okay, so A is the total force and the tension is equal to the total force and compression. And so A is 480 over 0.85, 4,000 PSI concrete, 18 inches wide. A is 7.84. And so Mn is, not Mn, I'm sorry, Mn, the capacity, is the tensile force 480 times D minus A over 2. So let's talk about D for a second. D in this problem and the next problem, a lot of folks had a little bit of a confusion about D and D sub T. And so I wanted to talk about that. First of all, D is defined as from the top of the beam to the centroid of all the steel. That's D. And D, in this case, is 25.5 plus half of that spacing, which would be plus an inch. So D is 26.5. That's to the centroid of the steel. However, D sub T, when you're checking epsilon sub T, D sub T is to the lowest layer, okay? And I spent a lot of time writing this on everybody's test. D sub T is 27.5, D is 26.5. It was a big source of confusion. I wanna make sure everybody's clear now that D is to the centroid, D is 26.5, D sub T is to the lowest layer, the centroid of the lowest layer, and that's 25.5 plus 2, 27.5. Okay, do I have any questions about D or D sub T?
No, no, now it's more clear. I had this confusion on the test.
Okay. Okay. And that's one of the big reasons I wanted to go over this. So, and remember, when you're doing these types of problems, you have to be careful about what information am I giving you and how do you find, D and D sub T. Okay. So, Brandon, yes, they are. If the bars are one layer, then D and D sub T are one and the same, as they were on problem 3. So when we get to problem 3, you'll see that. Okay, I calc this out. I get 10,838 kip inches or 903.2 kip feet. Just a quick note here, the answer was not correct if you don't have the correct units. The units are just as important as the number itself. So I was looking for either 10,838 kip inch or 903.2 kip feet. Next part, what is the minimum steel? The minimum steel, it was acceptable to do either way. You could calc out the two equations, and the greater of the two is your minimum steel, and then show that this is less than the 8 square inches provided. That was acceptable. Or go to table A.13, A13, and on that table there, it has a minimum row. Row minimum is 0.0033, and then you could calculate what that area of steel was and compare that as well. Either way is acceptable, the table or these two equations. For the minimum width, that I used the table A.5, and I assumed number 3 ties. That gives me 12.02 inches. If you assumed a number 4 ties, that's fine. I forgot what the number was, but it's still way less than 18. So either way was fine if you assumed number 3s or number 4 ties, since it wasn't given in the problem. Okay, so do I have any questions? Yes?
Yeah, so a question regarding the ties.
Yeah.
Even though there are no ties on that figure, do we always assume ties will be present?
Yes, you do. That's a great question. Yes, you do. When we talked about shear ties, there are situations where you could have, like in the middle of a beam where the shear is so low, you don't need ties, but I've never seen a reinforced concrete beam with no ties, period. There's always ties at the end, and most often there's ties through the whole span. It's actually pretty rare that you don't have any ties. So to answer your question, yes, always assume there will be some ties. I just didn't show them because that's not part of the problem. Because the ties are for shear, and we weren't talking about shear in the problem.
Okay, gotcha. Thank you.
Okay. Any other questions on part B?
So for I use the checking of the minimum steel with using the row equation,
Yes.
and that equation is the area of steel divided by the bottom width times D, correct?
Okay, so yes, you can work it 2 ways actually. You can go to the table and find row minimum, and that's equal to 0.0033, and you can multiply that times BD, and that gives you the minimum steel. That actually will give you 1.59. Or, and you could do, or just as well, you could take the total area of steel, divide by BD, and that gives you a row, and then compare that row to 0.0033.
As long as it's greater than the row minimum, correct?
Correct.
Then it's okay?
Yep.
Perfect.
Yep. Okay, good questions. Anybody else?
Professor, for this one, when you said find minimum B width, did you want us to use the table or did you want us to use it by hand?
Either way was fine.
Okay, perfect.
Yep, either way was fine. Given, well, I certainly didn't say you couldn't use the tables. Yeah, either way is fine. I find that doing it by hand is actually riskier, there's more ways to go wrong. So we did it in homework problem 2, I think. I think from here on out, just use the table because it is a risk that you're going to miscalculate something. It's easier to just find it in the table.
Professor,
Got it.
so, oh, sorry. So in the table 8.5, there's 2 columns for different types of stirrups.
That's right.
How do you know that it was the number 3 U-shaped stirrups?
You don't. You don't. So when I graded it, you know it's going to be 3 or 4.
Correct.
And so when I graded it, I was looking for either 12.02 or I think it was 12.47 or something like that. And either one of them is perfectly fine. It just depends on which one you had assumed. Yeah, so nobody lost any points for grabbing either from number 3 or number 4.
So when it's not given, it's simply based on assumption, correct?
Yeah, yeah. Or if it's not given, I think I mentioned earlier, just assume number 3.
Okay, I'll take note of that.
Okay. Anybody else? Okay. So part C then is find the allowable moment capacity. And that's engineering slang for phi min. We're looking for phi min. But before you can give me phi min, you need to know what phi is. You can't just assume that it's 0.9. You don't know that. So you have to calculate little c, which is 7.84 over 0.85 was beta 1. That equals 9.22. Then you calculate epsilon sub t. Again, the biggest hurdle for most people was recognizing that this is different than d. This is d sub t. So this was 27.5. It was only worth a point, but yeah, it was a point if you missed this one. I got 0.0595 is greater than 0.05, therefore phi is 0.9. Then I just multiply 0.9 times my 903, and I get my A12.9. So, any other questions on part C? And yeah, Ashley, you make a good point. Yeah, I try not to kill anybody's grades, but you make a good point that you can see as we go through this test that there's many ways to miss just one number here or one number there. And trust me when I say I did try to go through. If you made a mistake in the beginning, I followed it through to not keep docking away. If it was just one mistake, you could have gotten 11 out of 12 points for the problem, even if your final answer was way off. The point was to try to find the misconceptions and then correct them before we move on with the rest of the course. Okay, so any other questions on problem 1? Okay, problem 2. Not that the problem was terribly more complicated, I just didn't have as much blank space here at the bottom, so I kind of scribbled all over it. But here's our T-beam. And please notice that other than, actually, well, the steel is given as well. I just changed it up between parts A, B, and C, D, but everything is given. The width of the beam, the effective width of the flange, thickness of the flange, overall depth, and the distance to the steel was all given. So this too is an analysis problem. And I also made the concrete 4,500 PSI. Why would I do that? Why would I make it 4,500 PSI?
Beta 1 is not equal to 0.8 or 0.85.
That is absolutely correct.
That was
And
the curveball of the century right there.
yes, it was. and it also prevented anybody from using the tables. So I wanted to make sure that you guys could work through some of these things without the tables. The 4,500 killed the tables. So, yep, no, you're right. That was a curveball. I didn't think it was too diabolical, but it was sneaky.
I just remember like reading how to solve for beta 1 when it's not equal to the numbers on the tables, and I was like going over the book during the test, like trying to find it to see where I can locate it. So luckily I was able to.
Right. Good, good. And I think most folks found it. There's a few trip ups there, but I think most people got to this. So if we had 4,500 PSI, we have 60 KSI steel, and if the 6 bars are number 8s, then is this a true T-beam or is it a rectangular beam? The test is the depth of A. So you find your total tension force, 6 times 0.79 for a number 8 bar, times 60 KSI is 284.4. A, 284.4 over 0.85 F prime C. This has to be the width of the flange. You can't put in the width of the web down here because the web's not in compression. The flange is. And you get 2.07. To fully get this correctly, you had to get the correct A, 2.07, but you also had to correctly identify that that is less than 3. So therefore, this beam behaves like a rectangular beam. And that's all I was asking for part A. Part B, what is the moment capacity of this section, VMN? Well, in order to answer this one, first of all, you need to know what phi is. You cannot assume that phi is 0.9. So in order to get phi, you have to calculate epsilon sub t. Epsilon sub t, you need C. C, you need A divided by beta 1. So here was the sneaky part. Sorry, guys. Nobody ever calls my phone. And I wish they, anyway. Okay, so beta 1 is 0.85 minus F prime C minus 4,000 over 1,000 times 0.05. And this is only valid between 4,000 and 8,000 PSI. Above 8,000, beta 165. Below 4 or at 4,000 or below, beta 1 is 0.85. So, but this is what you do for anything in between. This calcs out to 0.825. So C is equal to 2.07 divided by 0.825, 2.51 inches. And epsilon sub t is 0.003. Okay, here's 33.5. So the distance from the top of the concrete to the lowest row of steel is 31.5 plus 2, 33.5. That gives you 0.037 greater than 0.005. Therefore, phi is equal to 0.9. So then I can use, this is a rectangular beam, so I can use my flexural equation, 0.9, 284.4. D to the centroid of the steel is 31.5 plus 1 to get to the center. So that's 32.5 minus A over 2. And you should have 8,054 kip inch or 761.2 kip feet. Okay, so hopefully everybody who's listening to this, you have your tests in front of
Professor?
you.
Professor, I
Yes,
have a question.
please.
So for T, we didn't do individual bar times 6. We did the table. And some of them is because it's not exactly 0.79. It could be like 0.785. So our T was a little lower, making our VMN lower by 30 kips. Did we get points off for that?
By 30 kips?
Yeah, by 30 kip feet. Because our T is not 6 times 7.79. We used the table with the 6 bars together.
Okay, well, let me
I had
see.
the same problem.
Yeah, it will make our VMN lower than you by 30. We got 635.9.
Which table, please?
Let me go check. I'll do it right now. Give me a second.
Oh, table 8.4,
Yes, 8.4.
6 number 8s. 4.71. I have never seen this table before in my life.
And yours will give 4.74. So that 0.03 difference will.
Can't possibly. All right. Let's give the question its fair assumption here. 4.71 times 60 is 282.
Oh, it's not off by that much, but it will give a little bit difference.
Okay, well, I want to know how much that difference is before
Mine
I.
was off because I used the wrong D. I didn't add 1, but it'll be
Ah,
different.
no,
Yeah.
that will really do it.
Yeah.
Okay, so instead of 207, I got 205 divided by 2, 32.5 minus second answer, 3147 times, 282.6 times 0.9, 8,005 over 12. I am pretty absolutely certain nobody lost any points because they gave me 667 instead of 671.
And what if we just get the D wrong, but everything else correct? Does that mistake carry on and make us lose more points or no?
No. If you got the D wrong, then that was a point.
And any carry on mistake will not be deducted?
It shouldn't be. I mean, it's not too hard to follow through these calcs. I followed through and I didn't just keep whacking away every time something. No, I really took a lot of effort to try to find where the mistake was and then kind of track it down. And, sometimes there's 2 or 3 mistakes in the same problem that kind of compound each other. But I would track those down and take off a point for each mistake that I found.
Okay, thank you.
Okay, so but I mean that's a very valid point that I never use those tables. I just use, like you just see there, 6 times 0.79 times 60 is what I do. And if you use the table, then you were off by, let's see, minus 671.2 divided by 671.2.
Ashley is table A4.
Yeah, I got it. So you're off by 0.6%.
Yeah.
Where was that table? I never saw it. Yeah, I never saw it either, Ashley. Table A.4. Okay. Any other questions about parts A or B? Okay. I mean, don't be shy. If there's something you don't understand, now's the time. All right. So let's go on to part C. Part C said, find the correct value for A if instead of 6 number 8s, I have 6 number 10s. There's a point if I resolved A using BW, then C for max steel. Garrett, do you have a working microphone? I don't understand the question, I think. Oh, okay. All right. Did I lose a point if I resolved A using BW, which is 36, and then C for max steel? I don't see where max steel comes into this at all. The max steel should not come into solve C and then use C and checking epsilon T. No, you shouldn't have rho for max steel. So my C was 7.5. Yeah, you definitely lost points. Definitely. Yeah. C, okay, we're still on part B. So C can only be 2.51 inches. There's no reason to plug in maximum steel when the actual steel is defined. If that makes sense, Garrett. Yeah, there's no reason to even dream of what max steel might be when the actual steel was provided. So you check your actual steel against the maximum by calculating epsilon sub t. And because epsilon sub t was 0.370 greater than 0.005, then we have checked our maximum steel. But you don't solve for C using maximum steel. Did that explanation make sense? Okay. Okay. All right. So part C.
Professor,
Yes.
I have one. Oh wait, never mind. I see it. Never mind. I was looking at part C and part D, and I was a little bit confused about that part. Never
Okay.
mind.
Well, if you still are, then please ask your question. But let me go through it and then see if you still have a question. Okay. So if instead of 6 number 8s, we have 6 10s, everything else is the same, but we just substitute 6 number 10s. Find the correct value for A. So we start over at part C. So I'm down here now. In fact, let me get my little spotlight. There we are. Okay, so now I'm down here. And 6 times 1.27 times 60 is 457.2. I suppose it'd be a little different if you use that table, but pretty close. And then I calculate A is the tension over 0.85 F prime C times BW, but A is 3.32 inches. The important point here, the really important point here was that you recognized that 3.32 is more than 3. You can't have compression down here because there's no concrete. It doesn't exist. So you had to recognize that 3.32 was an indicator to tell you that A is completely bogus. It can't exist. So that means that it is going to be a true T-beam behavior, and you start over by calculating C sub F, 275.4 kips. That's the compression in the flanges. Calculate C sub W, which is the tension for the whole thing minus the compression in the flange, 181.8. And then with 181.8, solve for A using 0.85 F prime C. And now we're only looking at the compression in the web, so the thickness of the web is 12 inches. Your true A is 3.96 inches. Okay, now I think lots of folks had some difficulty getting from here to here. And I remember a few papers were missing this part entirely. So please, on part C, if anybody has any questions on how I got from the bogus A to the correct A.
So, Professor, you basically did for your CF. You just since you determined that because A was greater than H, now the entire flange is in compression, right? So now you have to sum up. You have to sum your tension, or I'm sorry, you have to say that the tension is equal to both the compression, the flange, and the web, right? Is that basically
Yes.
what you did?
Yes.
Okay.
No, you got it. You got it. Let me draw a pretty little picture here. C sub F is the compression here and here. So yes, you have fully activated the flange because little a was bigger than the flange. So the whole flange is completely activated, and that's what C sub F is equal to. This is the width of just the overhanging flange times the thickness of the flange, 275. Now the compression in the web is going to be here. And you know it's going to be deeper than the flange thickness because we already solved that it's deeper. So you know that this is A now. Okay, that's what I'm looking for, and I'm looking for that. So A is this distance here. And so you solve for it using the 12 here, because this is your compression area for C sub W, and this is only 12 inches wide. So Ashley, what you just said, absolutely, that you got it. Okay. For the first part with checking max steel. Okay. Garrett, I might have to answer your question offline. I'm still having a little difficulty understanding. Okay. Any other questions on part C? And again, the question was just looking for the correct value for A. A was 3.96.
Professor.
Yeah.
I determined a different way. I think it's the way that the book uses it. So
very unfortunate.
For part A and C, I was able to determine if it's a true beam, a true T-beam, or a rectangular beam by comparing the area and compression and the flange area.
Yes.
Is that an allowable way to determine it, or?
Yes, of course, because the textbook teaches it. It's not incorrect, and I told you to read the textbook, so that's not your fault. It is just my humble opinion that the way the textbook teaches that, it relies too much on indexes that you really can't visualize exactly what you're doing. So I like to teach it this way, because when I teach it this way, you can visualize that there's a compression force in the green area and there's a compression force in the red area, and you get to this. So the difficulty was, if you applied that method that they taught in the textbook correctly, then you should get the right answer. The problem is if you do not apply it correctly, or you have a misstep somewhere, it's very difficult for me to figure out what went wrong, because I don't really use that method.
Yeah, I got both values for A and C correct, but I was really confused because the answer, or I was able to determine it was a true T-beam, but somewhere in the problem, it was telling me that the neutral axis was still in the flange. So I was thrown off completely by that. And,
yeah, okay.
Yeah, I'm gonna take your advice on, solving these type of problems your way from now on.
But don't get me wrong. There's nothing wrong with the way the textbook teaches it. It will give you to the same right answer if you do it correctly. And of course, I'm not going to badmouth the professor who wrote the textbook. He wrote the textbook, for crying out loud. But it's just my opinion that the way I did it is more clear to understand. The steps are more understandable. But however you choose to do it, that is totally your prerogative, as long as you get the right answer.
There should be the 11th edition by Professor Pratt.
Yeah.
So, yeah. Yeah, I'm going to stick with your way from now on.
Okay. And again, for everybody, that's totally your decision. It's just, generally, how do I say this? It's kind of like the old joke. Which exercise is the best to keep you in shape and to keep you healthy? Which exercise is best? Is it, some people say running, some people say swimming, no, bicycling's the best, no. Well, you know what the answer is? Whichever exercise you actually enjoy is going to be the one that you're going to end up doing. So it's totally up to you. Whichever one makes the most sense to you, go ahead and use that method. It's perfectly fine. Thank you, Ashley. But I think we'll remember, I'm doing this for fun. Where are we? Part D. What is the value or is the value for epsilon sub t allowable without penalty? Okay, so really you just need to calculate epsilon sub t for this last part. And again, here's the tricky. You have to have d sub t in there. Instead of just d, you have to have d sub t. And then you just find that 0.1794 is greater than 0.005, so therefore you're okay. Okay, so do I have any more questions on problem 2?
Professor,
Yes.
how many? So I made a very stupid mistake.
I'm sorry.
Yeah, it's okay. Okay. So it's for the first part, part A. Sorry, for the first one, B. I when I was calculating MN, I don't know why I put the value of C in there instead of A, which makes no sense. So I pretty much did 2.48 divided by 2 instead of 2.7.
Uh-huh.
Uh,
Yeah.
how many points did I lose for that?
1.
1. Okay, perfect.
Yeah.
Because I
1
got
point.
the MN wrong. I was off by like 5 on the MN because of that.
Yeah, yeah. Did you take a point off every time we use D instead of D sub T? Let me see, how did I do that? I think what I did, and this is Garrett's question, before I answer that, I'm pretty sure that I did it once, but I did it once for D, and I did it again for D sub T. So that was 2 points if you got them both wrong, because some folks had a little issue with the way that this was written. Some people had 25.5 for D instead of 26.5. So there was a way to get confused about D, and then there was a way to get confused about D sub T. So I took 1 point off if D was wrong. I took another point off if D sub T was wrong. But if I did it once, I didn't do it again on the next problem. And then finally, Garrett, whatever I did it the same to everybody. Everybody got the same issue. Okay. Miguel, do we need a penalty? Oh, okay. I think I know what you're saying, Miguel. Because 0.1794 is greater than 0.005, then no penalty. Oh, of course. Okay, so is everybody got what they need, or?
For Professor, for part D, if we did the calculation and we found out that the value is without penalty, and we just wrote that line there, and we had everything else in our calculator, did you deduct any points off of that if we just have the answer?
So you didn't write this, but
Yes.
you wrote this?
I just wrote that the value, because the question was asking, is the value for ET allowable without the penalty? And I said, yes, it is without the penalty. That's all I wrote. And everything else I have on my calculator.
Did you tell me what epsilon sub t actually is? Did you give me this number?
No, no. I had it in my calculator.
I probably did then. I'm not sure, but I probably did. Because just the yes without any calculation showing it to me, I'm not sure what I would have done if this was missing, but if this was missing altogether and the answer was just yes, yeah, you always have to back up. You can't just tell me, you got to back it up with something. So that was probably a point.
Okay. Because I started with problem number 4, and then it was a written problem. So when I saw this problem number 2, part D, and also part A, then I thought it's fine to write just the final. You're looking for final answer.
Okay. Well, I mean, that's something we can look into deeper offline. I could try to dig through and maybe dig out maybe what I did, but without the comments, I mean, that was really my tool as well. But we could take it offline. That's kind of more of a how did you grade it type of thing instead of the theory of it. But in general, like right here, is this a true T-beam or a rectangular beam? If you just wrote rectangular beam and moved on, you lost a lot of points. In general, you don't just give me a yes or no guess. I mean, anybody could just guess 50-50, right? We need the calculations that prove that it's a rectangular beam. Okay, does that make sense?
Yeah, sure. For part A, I did show, but for part D, since I was running out of the time, I just wrote the final answer there to submit it like on time.
Okay, well then let's take that offline so we can get to the lecture that we're trying to do today, if that's okay with you.
Yeah, sure.
Okay, all right. Problem 3. We're almost there. We're getting there. Okay, so problem 3 was the design problem for the midterm. And the design problem, I did give you all the parameters of the section and everything, but I didn't tell you how much steel we had. And I gave you loading information in a span. So the question was, find the area of steel required for given loading. I gave you a very specific load case. Choose a rebar pattern, and I said use number 9s, and show that the capacity is greater than the demand. This is all part A. So you need to calculate the demand, 1.2 times 1 for the dead, plus 1.6 times 2.5 for the live is 5.2 kips per lineal foot. The equation for a simply supported, uniformly loaded beam is WL squared over 8. That gives you 665.6. If you chose to find your reactions and then solve with a shear and moment diagram, that was perfectly fine, as long as you got to 665.6. And then, here's where it got a little funny. So the procedure, when you know the depth, you know the width, all you're trying to find is how much steel do you need. The procedure is to calculate this index R sub n. Everything that goes into this equation is known. There's your moment, there's your width, there's D squared. So when you use R sub n, you get 0.373 KSI. And then once you get 0.373 KSI, you either look it up in the table or you calculate it with the equation that I gave you to come to a rho of 0.0066. When you have that rho, then you just use rho times BD to get the area of steel, 4.99, and then you choose an area of steel. I had all kinds of funny ways that people had tried to do this one. Not funny, creative, different ways that people try to do this. I will tell you right off the bat that some folks tried to use rho equals 0.18 F prime C over Fy. And I can understand how that would be confusing. But you don't use that if I gave you D. D is known. You only need something, you only need those targets that we talked about. The target was 0.18 F prime C over Fy, or rho when epsilon T equals 0.0075, or maximum rho, or anything like that. Those targets are only needed if you have no clue how deep the beam's going to be. In this case, the beam depth was defined. So the examples that I did in the lectures and some of the examples in the books are much more complicated because we didn't have a clue how deep the beam needed to be. and that's what you do. But if you know how deep the beam is, if you know what D is, you don't do or need to do any of that. It greatly simplifies it. All you need to do is calculate R sub n, find out this index, look it up in the table, or calculate it from the equation, and get an area steel. Then you choose an area steel that is equal to or greater than what is demanded. So I chose 5 number 9s. It's just barely more, but it is more. And once I choose 5 number 9s, from that point forward, this is a analysis problem. The design portion of it was just to get you to here. And now it's analysis. So the analysis, straightforward, goes through all the same steps every time. A is the area steel times 60 KSI, 0.85. Concrete is 4,000, beams 24 wide. A is 3.68 inches. The concrete is 4,000, so beta 1 is 0.85, so C is 4.33 inches. In this problem, there's only one row of steel, so D and D sub T are the same. D that I used here, 31.5, D sub T, 31.5, one in the same. So epsilon sub T is 0.188 greater than 0.005, therefore phi is equal to 0.9. Therefore, phi Mn, 0.9, 5, 60, 31.5 over A over 2 is 8,008 kip inch, or 667.4 kip feet. 667.4 is greater than 665.6, so therefore this is acceptable.
Professor?
Yes?
Okay, I have a question. This, if we're using 6 number 9s instead of 5, and then our VMN is still greater than MU, yeah, and
Yes.
the moment capacity is still works. Is it considered as, I mean, did we lose any point on it?
No.
As long as it's,
Well,
because
yeah.
6 bars also fit in the beam. In the
Yes,
beam.
yes, yes. Hold on a second. I want to answer your question. I want to answer your question correctly, so let me look up something here. It's homework 1. Okay, so no, I did not take away points if you chose 6 number 9s instead of 5 number 9s. And I ran the whole problem with 5 9s or 6 9s. And with 6 9s, A becomes 4.41, C becomes 5.19, and phi Min was 791 kip feet. So I ran them both ways. I wasn't, I mean, because look how close this is, right? And if you had a round off error in your row, it might push you over. So no, I did not take off any points for that.
I got this same, as you said, same numbers with number 6, with using 6 number 9.
6 number 9s, yes. And I do, in part B that we're about to get to, I did ask for that it fits in the minimum width and that your maximum and minimum steel requirements are met. So that's where if you had gone horribly wrong at some point and ended up with 20 number 9s, it wouldn't fit in the beam and you would have to tell me, we got a problem here, this doesn't fit. But if you gave me 5 number 9s or you gave me 6 number 9s, either way, there was no problem with that.
Thank you.
Okay, and yes, I'm sorry.
Let's say that I was able to determine the correct amount of number 9s, but everything after that was incorrect. How many points would you deduct from that?
Oh, hard to say. It all depends on where you went wrong. I had to, I'm not going to share it with you guys, but I had a pretty keyed up version of where I allocated points. And where most people, if you lost a lot of points on this problem, most people lost a lot of points because they missed this. They missed using the index R sub n and rho to get to this point. Like I said, after this point, everything below this is straightforward analysis. So if you made some mistake below this line, down in here someplace, I just evaluated it and took off a point for any independent error that I found.
So initially, I had calculated rho using the tables based on R sub n, and I knew that that wasn't getting me anywhere. So I used the formula for rho that you gave us, and
Okay.
I was able to determine that it was 5 number 9s after that.
Okay.
But everything after that was just incorrect. But honestly, I'm not sure if I actually changed it on the exam, because the first way I actually calculated that we needed 9 number 9s, and I was like, wait, that's not good. So then I used the formula for rho, and I got 5 number 9s, but I don't think I changed it on the exam.
Okay. Well, again, let's take that part offline, and I can kind of dig through and try to figure out what I did if you're interested. But you understand the theory.
Yes.
Okay. So if you understand the theory of what we did, then we can talk offline about actual points.
Okay.
Okay. And we got to wrap this up. Part B was, again, just to show that the steel that you chose fits into the given width and that the maximum and minimum steel requirements are met. So to my private question, I think this is answering your question. So I use tables. Tables okay? So I use tables. So table A.13, in the first problem, I calculated AS min, and I calculated the 2 different cases, and then I took the larger of the 2. That was perfectly fine. This time I used the tables to show how you would do it using the tables. So if you look up table A13, rho minimum is 0.0033. Rho is your actual steel, not your demand, your actual steel divided by BD to get 0.331. And at first glance, it looks like it's close, but remember, rho minimum is 0.0333, and your actual is only 1.0331. So it's by far larger than your minimum. Your maximum steel was checked right here. I just repeated it to show that it was checked, but as long as epsilon sub t is greater than 0.005, the maximum steel has been checked, and B minimum according to the table was 14.27 with number 3 ties. Again, I wrote down 4 numbers. I wrote down 5 number 9s with number 3s, 5 number 9s with number 4s, 6 number 9s with number 3s, and 6 number 9s with number 4s. Whichever one of those 4 you assumed, as long as you gave me the right number for that, then they were fine. Okay, any questions on problem 3? Okay, I do, without beating a dead horse, I do want to reiterate that it is important. It's important to everybody to understand that if everything is given to you, all you're missing is the steel, then this is how you do it. Just use the RN, find rho from the table or calculate, and boom, there's your steel. If you do not have something else, if you don't know how tall the beam is, you don't know how wide the beam is, if there's something else missing, then you start using those targets. But don't use the targets if everything is known except for the steel. if we did AS min using the equations, of course, yes, that would be perfectly fine, as long as you got the right answer. Okay, and last, why is too much steel dangerous? Okay, so I was pretty lenient on this one, but I was looking for some keywords here. Basically, I was looking for that the concrete will crush, but the concrete always crushes. Every beam failure is always concrete crushing. What's important is that the concrete will crush before the steel is going to yield. And if that happens, it's going to be a brittle without warning type of failure. Okay? So it has nothing to do with strength. It has nothing to do with cracking. It only has to do with that the steel does not yield at the time that the concrete crushes, and so it fails without warning. Those are the keywords. What is the absolute lowest value of epsilon t allowed by code? 004. What is the lowest value allowed before penalty? 005. What is the maximum strain in concrete before it crushes? 003. And what is the variable that defines the relationship of A to C? Looking for beta 1. Some of you out there, without naming names, lost 1 point. The only way that you lost 1 point on question D is if you told me beta and you missed the 1. So you missed 1 for missing the 1. Okay, so do I have any questions at all?
Professor?
Yes.
So you're saying the absolute lowest value allowable by code is 0.04, wasn't 0.03?
No, for epsilon sub t.
Yes.
Yes, epsilon sub t. Now, this is for beams. And we're about to start a new section on columns. So you're going to see it's different for columns. But for beams, and you go back to lecture 4, I think it was, but for beams, the code says you cannot be lower than 004.
That's probably why I got confused. Okay, thank you. Makes sense now.
Okay. And then, of course, 005, you have to be above 005, or you have to calculate a reduced P factor. And then again, C, the maximum strain in the concrete before it crushes, the American ACI code assumes 003. It's always 003. The Euro code is like 0035 or something like that, but that doesn't matter. We have to follow ACI. ACI, it's 003. Okay, any other questions?
Professor?
Yeah.
You said that you have to either be above 0.005 or calculate a reduced fee value. So it's
Yes.
not both of them. They have to be one or the other. Like you have to at least have one like requirement met. Is that what you just said? Because that part kind of confused me. Like when do you, if your E of T or epsilon E is less than 0.005 but greater than 0.004, that's when you change your phi value to that equation that you use?
Yes, that's exactly right. So let me try to say it just using different words. I think you got it, but let me just say it in different words. If epsilon sub t is less than 004, the beam is not allowed. You can't do it. If epsilon t is greater than 004, but less than 005, it is allowed, but you have to calculate a reduced fee. If epsilon sub t is greater than 005, then phi is equal to 0.9 and everybody's happy.
Okay, thank you. Yeah, that part kind of confused me a little bit.
Okay.
Thank you.
All right. All right, so as I've mentioned, we do have a lecture for tonight. So why don't we take a break? Let's meet back here 6:10, 6:11, and we will start tonight's lecture, okay?
6:11 sounds good.
Okay, 6:11. Okay, 611, right? So I forgot there's a couple other things I wanted to mention
Professor, I
before.
think you're on mute.
I heard you.
Never mind, I was on mute. Sorry.
Okay, now can you hear me?
Yes. Professor,
Yay!
you said something about the average and the standard deviation you were going to talk about.
Yep, that's what I forgot to talk about.
Yes.
Okay. Hold on a second. I gotta, just a second. Be right back.
Okay.
Can you close that, please? Great, thanks. Okay. Yeah, all right. So the average of the test was 36.5. And I do curve the tests. So the midterm and the final will be curved. So basically, if you got right around that average, somewhere around 34 to 36, 38, somewhere in there, that's basically in the C range, C plus range, somewhere around there. And you want to try to bring that up for the final, but it's definitely not the end of the world if you're still in the mid to high 30s. One standard deviation above that in the 40s is doing fine. If you scored 40 or higher, I mean, unless you're really gunning for an A plus or whatever, but you're in pretty good shape if you're a 40 or above. What I really want to say is that if you scored below the average and even into the 20s, you really need to pick it up. It's important that you understand that there's only one more big test, that's the final. And you really need to pick it up if you're in the 20s. If you were in the low 20s or even lower, this really needs to be a wake-up call. It's going to be very difficult for you to recover from a score that low. So say like the average -1 standard deviation is going to be difficult. And don't get me wrong, I'm not picking on anybody, but if that was you, please start getting a hold of me. Get a hold of me during office hour, or email me if you can't make it to the regular office hour. We can schedule another time. But I think you know what I'm saying. Okay, so that's the midterm and how I curve.
Professor, what do you, so the curve is just a grade curve, not a point curve?
No, I curve the points. So
Okay.
yeah, but I don't do it until I have all the numbers. Once I have all the numbers, then okay, so the curve is really meant to make up for something that wasn't clear on the test. Everybody misunderstood what I was looking for, or I said something in a lecture or on one of the presentations that was confusing and it confused everybody. The curve is to make up for that, right? So all boats rise and fall with the rising tide. If I messed up and I never covered something and then I tested you on it and everybody lost 5 points, well, that's what the curve is for. Bring everybody back up. Does that make sense?
Yeah, so that means for this midterm, there is no curve, technically.
I didn't say that.
Oh, okay then. Never mind.
I didn't say that. But I don't know how much of a curve there's going to be until I finish the whole thing and get all the numbers.
Oh, got it. So it's not done yet. Thank you.
Oh, no, not done yet. It's kind of like bowling, right? When you bowl a strike, you're not done yet. You got to see what you got in the next 2 frames before you know really what you got.
Makes sense.
All right. Now, the other thing is, it was brought to my attention that in the homework that I just gave, homework number 6, and I apologize. Right up front, I forgot to change this. In the homework, I had something called a transformed moment of inertia, or I sub t. If you see I sub t, just use I gross, I sub g. If I do this again, if I miss it someplace and you ever see in this class I sub t, just make it equal to I sub g. What had happened was, I've taught this course dozens of times, and every time that I teach it, I kind of just review what I taught, and I said, well, I mean, the subject of concrete design, I could teach this to you for 5 years, and I still wouldn't hit everything that I'd want to talk about. There's a lot to it. So obviously, every time I teach it, I kind of filter what's important, what really will the students benefit from, what is the point that I really want to get across, and what are some of those things that technically you could do this or this or this, but it doesn't really add much to the course. And I found that it confuses people in the past. So I've changed how I teach it every time by trying to evaluate what is just confusing and not really important and what is really important. And one of the things that I changed was to transform moment of inertia. I used to teach that. All it is just a refinement on the moment of inertia of a beam before it cracks by transforming the steel. And I decided I confused more people than it actually helps, so I got rid of it. But I forgot to erase it from the homework. So long way to say that if you see I sub t in the homework, just assume that I'm meaning I sub g, the gross moment of inertia. Okay, are we ready for tonight's lecture?
Yes, we are.
All right, I was waiting for somebody to be alive. Okay. Tonight is going to be the first of several lectures that we're going to do on column designs. Columns are somewhat complicated. So we're going to break this up into several lectures, but tonight's going to be an introduction to column design. A reinforced concrete column, and this is by definition. A reinforced concrete column is any concrete member that supports an axial load per ACI 318 section 9331 greater than 10% or 0.10 F prime C AG. Okay, so I just said a minute ago that if you're designing a beam, that epsilon sub t cannot be below 0.004. Just said that. Well, what is the definition of a beam? The definition of a beam is any concrete member that has an axial load less than 10% of F prime C AG. If it has more than 10%, then what you're looking at is a column. We will divide our study of columns into 3 categories. We're going to have columns with low eccentricities, load eccentricities, low enough to consider them concentrically loaded. So basically columns with just axial load, no bending moments. Or columns with a significant load eccentricity moment, but that will fail due to material limits. They're called a short column. So those have axial load with some moment, but it's still going to crush the concrete before anything else happens. And then finally, we have columns with significant load eccentricity and slenderness that the columns might buckle prior to achieving full material strength. It is estimated that roughly 90% of all braced columns and 40% of unbraced columns are designed as short columns. So the slenderness problem is somewhat rare in the braced columns. What is a braced column? A braced column is one where some other building element keeps the column from side sway, typically shear walls or moment frames elsewhere in the building. The floors then act as diaphragms to tie the braced columns to the lateral force resisting system. So a column that is braced has something grabbing it, usually a concrete slab, so that that column is not allowed to sway out of plane because it's tied then to some walls or moment frames or something else that is designed to keep the building stable. If a column is reliant on its own stiffness to prevent side sway, such as a column that is part of the moment frame, then that column is considered unbraced. ACI 318, section 625, defines a column as braced if bracing elements resisting the lateral movement of a story have a total stiffness of at least 12 times the gross lateral stiffness of the columns in the direction considered. It shall be permitted to consider columns within the story to be braced against side sway. Rarely, if ever, do I calculate a total stiffness of at least 12 times the gross lateral stiffness of a column. It's usually pretty obvious if it's braced or not. Today's lecture will focus on concentrically loaded columns where the applied axial load does not produce appreciable moments. Okay, so there are three basic types of columns, two of which are the most common. The first is by far the most common and typically economical, the rectangular tied column. So here's our column. It is in the shape of a square or a rectangle, and it is tied by these hoops here. These ties, hoops or cross ties that tie everything together inside the column are known as ties. And from a side view, you can see the main steel runs up and down the whole height of the column, and the ties are spaced at a spacing S, which we will figure out what that is later. So it's kind of like the same thing as a beam, where a beam had flexural steel and then it had shear ties. Well, a column has longitudinal steel and ties, and the ties are going transversely. For columns, ties do resist shear, but they also do a very important function of confining the concrete so that as you load this thing in compression, it tends not to bulge or try to burst the concrete out. It holds and confines it together. The main steel runs the height of the column and is an integral part of the flexural axial response of the column. The ties are for the shear response of the column, as well as a very important function of confining the concrete in compression. The second type of column is known as a spirally confined column. These are generally round, but they can be rectangular as well with interwoven spirals. So here we have a round column, and the tie that you see in here actually is not a tie, it's a spiral. And you can see how I've drawn it here. It's like a helix. So I don't know. When you guys were all kids, did they still have slinkies? And you push them and you watch them go down the steps?
Yeah, I love slinkies.
Yes.
Okay, great. Then you know what I'm talking about. This is a slinky. It's basically just a wire or a rebar that has been bent into a round shape, but it's in a helix. So you put it in the form or the bed and you pull it apart till you get the right spacing, S here, or pitch of the spiral. So it's basically a steel slinky that you use in the concrete. These perform better than the rectangular tied because these tight spacings or pitch of the spiral, and that it's not interrupted, it's continuous all the way up, gives it better performance capability. Okay, so the spiral is a continuous helix of rebar or wire. Spiral confinement provides a superior confining effect and is rewarded in ACI 318 with better capacity values. Spiral columns are generally more expensive than their tied counterparts, which is why you get a bonus in the design factors, but it doesn't actually overcome that they're so expensive to build them. So they're not rare, they're just maybe, I don't know, 30%, 25%, whereas the rectangulars are most of the columns that you'll see. The third type is a composite column, which is relatively rare, especially here in the US, but is used occasionally. And this is called a composite column. And so here we have a rectangular column, we have longitudinal steel, and we have ties. So all of that is the same. It's just that they bury this big old fat wide flange right down the middle of it to greatly enhance its axial load carrying capacity. So again, these are somewhat rare, but you might run into one. A composite column is reinforced similar to a rectangular tied column, except a structural shape is embedded to add to the total capacity of the column. This type is addressed by, and then you can look up all these references if you have interest in this type of column, but I found all the different sections that modify what you have to do if you have a composite column, which are, of course, beyond the scope of this class.
Professor,
Yes.
would you please give us like one or two examples of where they're used, like the different columns? I just don't understand how they're different and how, like for the first one, how would you use that, and for the second one, how would you use that? Is there like a difference in the structure? Is that why you use different ones?
No, there's economic reasons and there are architectural reasons. So there's a lot of places where round columns are preferred architecturally. That's the look they want. And there are places where nobody cares. So put in the cheapest kind of column. That's a square or rectangular column. Okay, so examples. Do you remember long time ago, you used to go to this place in Pomona called Cal Poly, and you used to park in this big old giant concrete parking garage. You remember that?
Yes.
I know. I have a hard time remembering what that was like, but yeah, we used to go to this place. And you go into that concrete parking garage, and it's all concrete, obviously, but the columns are rectangular concrete columns. Okay, so those columns look like this. If you were to peel away the cover concrete and looked at inside, this is pretty much what you see in all those columns in the parking garage. So that's this type, and that's very common. These guys, now it actually has been, I know I'm kidding, but it actually has been a really long time since I've been in the CLA building. Like maybe when I was a student and I had to go in there and pay my student fees or whatever. It's been a long time, but I think they had round concrete columns in there. And that was more for, it's an office environment, and architecturally the round columns were preferred for the shape over square columns. And then the third kind, this guy here, I only really know of, for sure, I know where these have been used once, and it was in Japan, and they had office buildings going 40 plus stories. And in Japan, it was more of a common thing that where the loads were really high in the column were towards the bottom of the building. They put these big wide flanges in there to pick up the extra load. But as the load dropped off, as you go higher and higher up the building, you have less load on that column. Well, they would discontinue this interior steel portion and just continue the exterior concrete portion. And it seemed like a great idea because you would just put a lot of steel where you need it, and you just drop it off when you don't need it. But it actually became a real problem in the Kobe earthquake, because where they stopped the steel, there was a sudden discontinuity of stiffness, and the earthquake just ripped the buildings apart right at that level. So every one of those lost a story. I mean, if they discontinued this steel on the 20th floor, the 20th floor disappeared. It was pretty dramatic. Oh, also, these columns here, Look at your, I mean, if you ever go outside again, look at your Caltrans concrete overpasses and those giant 8 to 10-foot diameter columns that are holding up the freeway. Perfect example is the 10, the 57, and the 71. That's a 4-level interchange. And when you're on the 10, you're on the bottom level. So you drive by and you see these columns are like 8 feet in diameter. Those look like this, but for a completely different reason. Those look like this, not because anybody at Caltrans gives a hooey about what their columns look like. It's just that these types of columns with this confinement perform better in earthquakes. So that's why all the freeway overpasses, they're either round or they're like a hexagon, which is structurally pretty close to being round. Okay,
Sure.
yes.
Just, I was always curious because at a job site I'm at right now, I know they're installing some geopiers underground, and I always wonder, do you ever, or is there any times where they could actually use columns underground to support foundation and slab on grade versus piers?
Yes. Yeah. They're concrete columns, but they go by a different name. They're called piles.
Okay.
Yeah.
Okay.
And not to punt your question, but piles are beyond the scope of this class. They're actually designed differently. There's kind of like different rules for designing concrete below grade from above grade. There's different ways that, because they're not actually called columns anymore, they're called piles. So they follow different parts of the code. But yeah, absolutely, yeah. And they have precast piles where they cast the whole pile at a plant and then drive them out to the site and actually drive them into the ground.
Awesome.
Let's see what Ashley's asking. I was curious about the failures of these, and I found that there was a failure of the columns of the 110 freeway at Venice Boulevard in LA failed due to an earthquake. I think that was the 10 freeway. Yeah, I-10. Yeah. That was different. That was because the columns punched right through the deck and they didn't have sufficient punching shear capability. So the columns were fine. The whole freeway fell around them. But no, they've had some very serious failures during earthquakes. Northridge, up there just before you get to Valencia, right where the 5 and the 14 come together, they just can't seem to get that to stay up. They lost a huge overpass in the San Fernando quake, and then they rebuilt it and lost it again in the Northridge earthquake. So yeah, that's what this is all about, is getting those freeways to have enough ductility to survive the earthquakes. Yes. And then also, I was up in the Bay Area for the Loma Prieta quake, and they lost a bunch of freeways in San Francisco for the same thing. Oh, and the Cypress Freeway in Oakland. Sadly, I mean, in all due seriousness, that was very sad. In the Loma Prieta quake, we lost over 200 people, and most of them were on the Cypress Freeway. And the Cypress Freeway was such a catastrophic failure because the columns were holding up an upper deck directly above the lower deck. And the columns that were holding the upper deck above the lower deck didn't have the ductility that I'm talking about with these spirals. So they exploded right here in the middle and dropped the upper deck onto the lower deck and lost a lot of life because of people got crushed. So anyway, not to go off into a sad direction, but that's part of why you see what you're seeing here. Okay, so carrying on, now that everybody's depressed. That's that column. Talked about that. Okay. As mentioned, spirally reinforced columns have superior confinement properties, which give the columns superior load to deformation properties. So what I've drawn here, and I think I got some commentary. Okay, so the initial load capability of comparable spiral confined columns to a tied column, it's very comparable. But what happens with the tied column is once it reaches its maximum, it doesn't carry on very much beyond that. Once it gets to the point where the column's basically falling apart, it just fails. But with a spirally reinforced concrete column, it kind of hits the same maximum, and then it goes long out here, but then because of the confining effect of all those spirals, it actually gets a second wind and actually kind of carries a little bit more load. We don't count on this extra load that it carries, but the benefit is look how much more deformation it can survive without dropping the building, basically. These are generally holding up buildings. So as mentioned, spirally reinforced columns have superior confinement, which give the columns superior load to deformation properties. Here's a picture. Okay, so this is what I'm talking about. This image is from 1972 San Fernando earthquake and at the Olive View Hospital. You can look this up if you're interested. This is like one of those case studies of what and what not to do in concrete design. This column was very, very poorly confined by very sparse rectangular ties, which if you can see the image, there's a tie right there. There's another tie down here, maybe one there, maybe one up there. The codes have changed dramatically since they built this building in the late 60s. But you can see this column did very poorly. It just exploded. It just completely fell apart. All the main longitudinal steel here is completely buckled and useless. And basically what we call this situation is just a box of rocks. That's all you have left. This column has no axial supporting capability whatsoever. And by the way, as you can see from this drift, look how far the building has drifted over. You can see the mullions are bent over. This thing's got like 1.5 feet of drift. What about Y column compared to the two you mentioned? Oh, I'm sorry, what's the Y column, Zarni? Zarni, if you're still there, I don't understand the question. Oh, I see on 110 freeway to downtown. You mean the column shaped like a Y? Y concrete beam. Okay, well, let's, is the column shaped like this, or is the column shaped like this? This is lens 1, this is lens 2. I think 1. Okay. Well, if it's 1, then it was probably built back before the 72 earthquake, and it's a disaster waiting to happen. Maybe. If it's shaped like number 2, then this is a capital that increases the punching shear capability so that the column doesn't just go right through the deck. I suppose this could be properly designed, but I don't think you'd see this on anything modern. It's just way too many problems with this, with seismic. So yeah, please keep that in mind, that what you see in the real world, maybe this is worth noting, please keep in mind that what you see in the real world is spanning over many, many years. So you could drive from the Inland Empire to downtown LA, and you could see overpasses that were designed in the 2000s, which should do pretty good. And you can see stuff that was designed in the 50s and the 40s, right? You know, the 110 freeway between the Pasadena freeway between downtown and Pasadena that doesn't actually ever make it to Pasadena. That's the country's oldest freeway. That was designed and built in the 30s. Remember Eisenhower put together the interstate program in the late 50s. So a lot of what you see is from the 50s and the 60s. And then, you know, every year thereafter. If it was designed before like the 90s, maybe, it's maybe kind of sketchy because they really just didn't have these things, weren't really thought out before the 90s. And if it was designed after the 2000s, it should be pretty good. Okay. Supporting fast track. Okay. Okay, so this is an example of what a tide column looks like when displaced by severe seismic. And now we can contrast that to, here's a spiral column. And you know what? This column, how different the behavior of this column is. This is on the same building. So this image is from the same building in the same seismic motion. The contrast is that this column was spirally confined, and even though it's deformed excessively, there's that same about 1.5 feet of deformation there, it's still supporting load. It's still supporting this axial load from above. See how closely spaced those spiral wires are? So even though all the cover concrete is completely gone, it's still keeping the concrete inside together and still supporting load. So this is what they mean by these superior confining qualities of spirally reinforced concrete. Here's a close-up of that spiral column. These bars here, we don't do that detailing anymore, but those were kind of just anchoring the top into the cover concrete, and they're gone because the cover concrete's gone. But here you can see all the spirals, and everything inside the spirals is still pretty much there. Okay, so let's get to axial load capacity. Very few column designs will actually be designed with pure axial load, no applied moment. But for the examination of column mechanics, we will start with the pure axial load case. So in other words, we're going to idealize these columns to say that there's no eccentricity, there's no applied moments. How would this column actually fail? So the factored axial load demand is found using the load factors presented in lecture 4. So the same load factors you've been using all along, we use those here. Like for flexure and shear, the allowable axial capacity phi Pn must be equal to or greater than the factored demand P sub u. So phi Pn must be greater than P sub u. For a column capacity, ACI 318 section 22422 specifies that P naught, that's how we say this here, P naught is the nominal strength of the column with no reduction for eccentricity as P naught, and this is just purely axial capability of the materials. So 0.85 F prime C times the area of the concrete minus the area of the steel plus the yielding strength of the steel times the area of the steel. So this equation assumes that all the concrete crushes and all the steel yields all at the same time. And again, this is what I mean by P naught. P naught is the nominal strength of the column, where AG is the gross area of concrete, AST is the total area of steel. P naught represents the maximum load that a column can carry, where all the concrete is crushed uniformly whilst all the steel yields. This is an ideal case. ACI 318 section 2.2 calls P naught the nominal axial strength at zero eccentricity. Okay, this is important. This is a definition. P naught, nominal axial strength at zero eccentricity. ACI code used to impose a minimum eccentricity on our designs, so that columns were designed with a minimum moment. But now the code from table 22421 only puts an additional factor to account for the minimum eccentricity. So in other words, instead of what they used to do is even if your moment was very little or nothing, they used to have a minimum moment that you had to design for. Now they don't. If your moment is little or nothing, that's fine. But what they do is they put another factor restricting the total capacity to account for accidental eccentricity. For tide columns, Pn is equal to 0.8 times P naught. And for spiral columns, Pn is 0.85 times P naught. For columns with pure axial load, the extreme strain in the steel will be compressive. Epsilon T will be less than 0. Okay, so before I jump away from here, Pn is the nominal axial strength of the column. P naught is the nominal axial strength at 0 eccentricity. So that's the difference between the two. Pn has a minimum eccentricity built into it. P naught does not. Therefore, because the strain in the steel will be less than epsilon T sub y equal to positive 0.0207 for grade 60 steel, ACI 318, 2122, and table 2122 prescribe phi as for tide columns 0.65 and for spiral columns 0.75. No. A question was asked, 0 eccentricity is before the slinky is stretched. No, this has nothing to do with the ties. Let me do it this way. And that's a good question. Thank you for asking. So here's my column. And if I have no eccentricity, I drew it the wrong way. If I have 0 eccentricity, that means your load is going right through the middle of the column. There's no moment. It's just pure axial load all the way through the column. But if I have eccentricity, which you almost always will, then what that means is that the load, and I'm greatly exaggerating it, but the load is way out here. So now you have an eccentricity equal to the distance from the center of the column to the center of the load. That's E, your eccentricity. And what you're going to get, I'm going to try to freehand this, but you're going to get a, no, I didn't want that. Sorry. You're going to get a bending moment that tends to bend this column over. So now you have moments and axial load on the same section. And that's what you usually have because, because you have a moment arm. Okay? Now, the point that I want to make here is I just got done telling you all, never, never, never can you have epsilon sub t less than 0.004. That is for a beam. For columns, not only is it going to be less than 0.004, but that's less than 0.004 in tension. Columns can actually have the steel in compression. So not only is it less than 0.004, it's less than 0. It could be minus 0.02 something. So what I'm trying to say is that if the strain in the steel is less than 0.0, I think they yield 0.002, then your phi factors really take a hit. And this applies to most columns, that your phi factors are much lower than for bending. Bending is 0.9 or 0.9. For columns is 0.65 or 0.75 because your strain is so low. It's actually in compression, okay? And the phi is also very low, 0.65 or 0.75 because of the consequences and the suddenness of the failure. If a column were just suddenly to explode in a building, the whole building would collapse and nobody would have any warning. So obviously that's very, very serious. So we have a very conservative phi factor. The phi factors are for compression controlled columns, which are purely axially loaded columns, always will be. Okay, well, when we get to columns with combined axial load and moments, then we will have to evaluate the magnitude of epsilon sub t to see if the column is compression controlled in a transition or tension controlled, which will then determine the phi factor. And all of that has nothing to do with how you built the column. It has to do with the loading. The relative magnitudes of axial load to moment will determine the epsilon sub t factor. Thus, the same column under different load cases may have different phi factors. If your load case has all axial load and very little moment, then your phis are going to be like this. If your column has very little axial load and a lot of moment, then it's going to behave much more like a beam, and your phi factors will be 0.9 like a beam. So the load condition is going to determine the phi factor. Okay. Example? Guys ready for example? Here I have a 24 by 24 column with 8 number 8 steel. Given that the concrete is 6,000 psi, the steel is 60 ksi, axial load is dead is 800 kips, live load axial is 350 kips, and my, remember this is my SDS factor for seismic is 1.45 Gs. Column has 0 applied moment. What is required, find the allowable axial capacity, and is this column acceptable to carry the given loading? Okay, so we have 2 parts of this. We need phi PN and we need PU for the loading, and then we can compare them. Solution. Let's first find the factored axial load, P sub U. P sub U is either equal to 1.4 dead, which is 1.4 times 800, 1120 kips, or 1.2 dead plus 1.6 live, 1.2 times 800, 1.6 times 350, 1520 kips, or it's equal to 1.2 plus 0.2 SDS times dead plus only 1 times the live, and that gives us 1542 kips. So in this case, the one with the seismic component is going to control. So PU is 1542. Solve for P naught. P naught is, this is now without any eccentricity. This is just the material properties. So yes.
You kind of lost me in that first step, or when you just said that column has 0 applied moment. Is that something you're assuming, or is that something that you know? And how do you know that?
I know that because it's part of the given.
Oh, that's part of given. Okay, I thought your problem started there. Okay.
So the given, all of this between given and required, all of this is given. So no, I am not asking you to assume anything. If it has a moment, we'll calculate what those moments are. If it has 0 applied moment, then M sub U is equal to 0. So the first, okay, so the first lecture is only dealing with columns that have just axial load. We haven't built the tools yet to deal with columns that have moment. So this is part of the problem, that it has no moment.
That makes sense. Thank you.
Okay, and you're good with the 3 load cases?
Yeah, this is basically from the previous chapter, but just with the P's instead of the W's or the
Yes.
U.
Or the M's or the V's. Yeah. Uh-huh. Okay. So my demand is 1542. Now I'm working on my capacity. So you start with P naught. P naught is 0.85 F prime C, AG minus AST plus FY AST. So AG is 24 by 24, 576 inches squared. AST is 8 number 8s. So 8 times 0.79 is 6.32 inches squared. So I just plug them all in, 0.85, 6 KSI, gross minus steel plus 60 KSI times the steel. I get 3285. But don't get too cocky yet. Just because 3285 is over twice my demand, that don't mean nothing. Wait till you see how these factors are going to knock this down. This is P naught. This is theoretically how much load it would take to completely crush the column with no moments or eccentricities. But the code doesn't allow us to do that. We have to solve for our nominal capacity P sub n. Because this is a tied column, P sub n is equal to 0.8 P naught from the previous slide that we just had. So 0.8 times 3285 is 2628 kips. So now this is my allowable capacity, including some eccentricity. But this is still nominal. I'm sorry, this is not allowable. This is still my nominal capacity. My allowable capacity is now times phi. So 0.65, because it's a tied column, 0.65 times Pn is 0.65 times 2628 is 1708. Now, we're still okay. 1708 is greater than 1542, so the column is acceptable, but good gravy. Look, we went from 3285 to 1708. Theoretical to allowable. Okay, any questions on this example? Okay, so let's look at some code requirements. And we're going to go to, because we kind of spent a lot of time on the midterm, so I'm going to try to go to 705, and then wherever we end up, we'll pick it up next time. So percentage of longitudinal reinforcement by code, ACI 318, and chapter 10 now is our column chapter. So 10.611, the area of steel AST shall be greater than 1% of the gross area, but less than 8% of the gross area. They have to fall into this. It's kind of like our minimum and maximum for beams. It's just a little easier to calculate for columns. If the column is part of the lateral force resisting system, part of a moment frame, then ACI 318 and chapter 18 is the seismic chapter. So you always gotta, you can read what you can do in chapter 10, but you always gotta check chapter 18 to see if there's some additional restrictions if you're building in seismic country. And if you're building in California, you're building in seismic country. So chapter 18 says that you have to be less than 6% of the gross area. If the main steel will need to be lap spliced within the column, then generally the steel should not exceed 4% of the gross area, because at that point that you lap it, you're basically doubling up your steel. And we'll talk about that later when we get to splices. For design economy, less steel and more concrete should be used when possible. For column designs, raising F prime C adds directly to the column strength. So that actually is very useful. In a beam, going from 4,000 to 6,000 PSI concrete helps a little bit. In columns, it helps a lot. It's directly proportional. Minimum number of longitudinal bars. ACI 318, section 10731, prescribes the minimum number of bars as follows. 3 if you have a triangular tie, which I have yet to see. You have to have 4 minimum bars if you have a rectangular or circular ties. And you have to have 6 minimum bars if you're enclosed by spirals, or for columns of special moment frames enclosed by circular hoops. Additionally, ACI 318, section 18752, items E and F restrict the maximum space in the longitudinal bars for columns resisting seismic forces. These provisions also apply to columns supporting gravity only in structures of seismic risk categories C through F. In other words, look in chapter 10 for what you can do, but always bounce off of chapter 18. There's additional restrictions. So while this provision does not dictate a number of bars, it effectively requires more bars in buildings built in regions of seismic risk. For 24 by 24 columns in California, the minimum number of bars becomes 8 or 12, depending on the magnitude of the axial load. Not more than 8 years ago, 6 years ago, 8 years ago, we were still building 24 by 24 columns with just 4 corner bars, 4 number 11s. And because of all this stuff that they've put into chapter 18 now, we can't do that anymore. There are always at least 8 bars, and now sometimes we have to go to 12 bars. ACI 318.752 will be discussed in more detail below. Tie requirements. Okay, so the minimum size of the ties, ACI 25722 gives us, the minimum size of ties is predicated by the size of the longitudinal steel. The minimum tie for a number 10 or smaller is a number 3 bar, and for number 11 or larger, or for bundle steel, is a number 4 bar. Now here's where I actually take a little bit of exception to something that the textbook said. The textbook applied this rule to beams as well. And they said, well, if our flexural steel is number 10s or smaller, then our shear ties are number 3s. But for 11 or larger, we can use number 4s. That doesn't actually apply to beams. That only applies to columns. Maximum spacing. The tie spacing is prescribed by ACI 318.2572 in accordance to A and B. Clear spacing has to be at least 4/3 of the diameter of the aggregate. The center-to-center spacing shall not exceed the least of 16 longitudinal bar diameters, 48 diameters of the tie bar, and the smallest dimension of the member. Okay? This rule right here applies to everybody in the entire country except us. So you go anywhere else in the country and you watch them tying up columns, and they got this pathetic little number 3 tie spaced at like 18 to 20 inches apart. Kind of like the photo of that destroyed column I showed you from all of you. And then you go and look at columns that are being done in California, and they're like 4 to 6 inches apart with double hoops and everything. It is dramatically different here from everywhere else in the country. Okay, I have 1 minute left. So if anybody has any questions to what we've done so far. And so if not, I release you with 1 extra minute to enjoy your lives. I will see you all on Thursday.
Thank you, Professor. Have a great day.
Thank you.
Thank you.